Imagine a lifeless, barren world, a stark contrast to the vibrant blue and green marble we call home. Now, picture that same desolate landscape transformed, teeming with life, rivers flowing, forests sprawling, and a sky painted with swirling clouds. This isn't a scene from a sci-fi movie. It's the potential future of terraforming, the process of making other worlds habitable. In the next 15 minutes, we'll journey through the incredible process of atmospheric processing, witness the transition from barren to green, and explore the long-term timeline of this cosmic endeavor. Stick around, because this isn't just about science fiction. It's about the future of humanity, and it's closer than you think. The cosmic frontier beckons. The cosmos is vast and mostly inhospitable, but the dream of making other worlds habitable has captivated scientists and dreamers alike. Terraforming, the process of transforming a barren planet or moon into an Earth-like world, is a complex and long-term endeavor. It involves a series of steps that can be visualized as a transition from a desolate, lifeless landscape to a lush, green paradise. The journey begins with the most basic of changes, altering the atmosphere. Atmospheric processing is a critical first step in terraforming. Many potential candidates for terraforming, such as Mars, have atmospheres that are too thin or composed of the wrong gases to support human life. On Mars, for instance, the atmosphere is primarily carbon dioxide with only trace amounts of oxygen. To make it breathable, scientists propose introducing oxygen-producing organisms like cyanobacteria or using technological means to convert carbon dioxide into oxygen. This process would take decades, if not centuries, to achieve significant results. The goal is to create an atmosphere that not only supports human life, but also protects against harmful radiation. Visualizing the long-term timeline of terraforming involves understanding the scale of the project. It's not something that can be accomplished within a human lifetime. Instead, it's a multi-generational effort that requires sustained commitment and technological advancements. For example, melting the polar ice caps on Mars to release water vapor into the atmosphere would take centuries. This water vapor could then contribute to the greenhouse effect, warming the planet and making it more hospitable. Over time, the increased temperature could allow for the introduction of plant life, which would further enrich the atmosphere with oxygen. The transition from a barren, red planet to a green, habitable world is a slow but steady process. Each step builds on the previous one, creating a feedback loop that gradually transforms the environment. A symphony of science and imagination. Terraforming, the process of making other worlds habitable, is a captivating blend of scientific endeavor and imaginative vision. At its core, it's about transforming barren, inhospitable planets into lush, Earth-like environments. Picture Mars, with its rust-red deserts and thin, unbreathable atmosphere. Over centuries, through a combination of technological intervention and natural processes, this desolate landscape could be painted green. The initial stages involve introducing hardy, genetically modified plants and microorganisms. These pioneers of life would begin the slow work of converting the Martian soil into something more fertile. They'd also start the process of atmospheric processing, releasing oxygen and other vital gases into the air. Atmospheric processing is a critical component of terraforming. On Mars, this would involve releasing greenhouse gases to warm the planet and thicken its atmosphere. One proposed method is to release CO2 and other gases from the planet's polar ice caps and soil. This would not only warm the planet, but also provide the raw materials for photosynthesis. Over time, as the atmosphere thickens and the planet warms, liquid water could flow on the surface, further aiding the growth of plant life. It's a slow, deliberate process, but one that could eventually lead to a self-sustaining ecosystem. The timeline for terraforming is measured in centuries, not years. It's a long-term project that would require sustained effort and investment. Initially, robotic probes and automated systems would do much of the work. They'd prepare the soil, release gases, and monitor the planet's progress. Eventually, human settlers would arrive, bringing with them more advanced technology and a greater understanding of the planet's needs. They'd continue the work of their robotic predecessors, gradually shaping the planet into a habitable world. It's a symphony of science and imagination, a testament to human ingenuity and our desire to explore and understand the universe. The dream of a second Earth. The notion of finding or creating a second Earth has captivated human imagination for centuries. It's a dream rooted in the desire to escape the confines of our planet, to find new homes among the stars. This dream isn't just about survival. It's about replicating the beauty and bounty of Earth, transforming barren worlds into lush, green paradises. The journey from a desolate, lifeless rock to a vibrant, habitable world is a complex process, one that involves altering the planet's atmosphere, temperature, and surface conditions. Atmospheric processing is a critical step in this transformation. Many planets, like Mars, have atmospheres that are too thin or composed of the wrong gases to support human life. To make these worlds habitable, we would need to thicken their atmospheres and introduce the right mix of gases. This could involve releasing greenhouse gases to warm the planet, a process known as terraforming. For instance, introducing fluorine-based gases could help warm Mars by triggering a runaway greenhouse effect, similar to what happened on Venus. However, this process would take centuries, if not millennia, to complete. Visualizing the long-term timeline of terraforming is a humbling experience. It's a project that would span generations, requiring patience, perseverance, and an unwavering commitment to the dream of a second Earth. The initial stages would involve robotic missions to prepare the planet, followed by the introduction of simple life forms like algae and bacteria to begin the process of creating a sustainable ecosystem. Over time, these pioneers would pave the way for more complex life forms, eventually leading to the establishment of a thriving biosphere. The transition from barren to green is a gradual one. It begins with the introduction of hardy, pioneer species that can survive in harsh conditions. These organisms would start the process of breaking down the planet's rocks and soils, releasing nutrients that would enrich the environment. Over time, these pioneer species would be joined by others, creating a complex web of life. The planet's surface would slowly transform, with deserts giving way to grasslands, and grasslands evolving into forests. This process, known as ecological succession, is a slow but inevitable journey towards a more habitable world. It's a testament to the resilience and adaptability of life, and a reminder of the incredible potential that lies within the cosmos. Mars, the red planet's redemption. Mars, the fourth planet from the Sun, presents a stark contrast to Earth with its thin atmosphere, extreme temperatures, and rust-colored, dusty surface. Yet, it holds the most promise for human colonization and terraforming among all planetary bodies in our solar system. The process of transforming Mars into a habitable world involves several key steps, with atmospheric processing being the most critical. First, the Martian atmosphere needs to be thickened to provide adequate pressure for liquid water to exist on the surface. Currently, Mars' atmosphere is about 1% as dense as Earth's, composed mostly of carbon dioxide. To increase atmospheric pressure, scientists propose releasing greenhouse gases trapped in the planet's polar ice caps and soil. This could be achieved through orbital mirrors to warm the planet or by introducing heat-trapping gases. Once the atmosphere thickens, temperatures would rise, allowing water ice to melt and flow, creating rivers, lakes, and possibly even oceans. The red, barren landscape would begin to transform, with water carving channels and depositing sediments, much like Earth's geological processes. Over centuries, the increased atmospheric pressure and warmer temperatures would enable the introduction of Earth's hardy plant life. Photosynthetic organisms, such as lichens and mosses, would be the first to colonize the Martian soil, paving the way for more complex plant life. These pioneers would convert carbon dioxide into oxygen, gradually making the atmosphere more breathable for humans. As vegetation spreads, it would stabilize the soil, prevent dust storms, and create a more Earth-like environment. The once red planet would slowly turn green, with plant life covering the landscape and releasing oxygen into the atmosphere. The long-term timeline for terraforming Mars spans thousands of years. Initially, robotic missions would lay the groundwork, followed by human settlers who would live in domed habitats while the planet is transformed. Over centuries, as the atmosphere becomes more Earth-like, open-air settlements would become possible. The process would be slow, requiring patience, persistence, and technological advancements. However, the potential rewards are immense: a second habitable planet for humanity, a backup for Earth, and a new frontier for exploration and scientific discovery. The Red Planet's redemption would mark a significant milestone in human history, demonstrating our ability to shape other worlds to suit our needs. Venus, a hellish transformation. Venus, with its scorching surface temperatures and crushing atmospheric pressure, is often likened to a vision of hell. Yet, beneath its inhospitable exterior lies potential. The journey to transform Venus into a habitable world is a monumental challenge, but one that scientists and futurists have begun to explore with seriousness. Atmospheric processing is the first critical step. Venus's atmosphere is composed primarily of carbon dioxide, with clouds of sulfuric acid. To make the planet habitable, this atmosphere would need to be significantly altered. One proposed method involves using orbital mirrors to reflect sunlight away from Venus, cooling the planet and allowing carbon dioxide to freeze out of the atmosphere. This process, known as solar shading, could take centuries but would be a crucial first step. Additionally, introducing air scrubbers or genetically engineered microbes could help convert carbon dioxide into oxygen, making the atmosphere breathable. The transformation wouldn't happen overnight. Over centuries, the once barren and desolate landscape could begin to change. With the atmosphere slowly becoming more Earth-like, the surface temperature would drop, allowing for the introduction of plant life. Photosynthetic organisms, both flora and genetically modified microbes, could start the process of terraforming. They would convert carbon dioxide into oxygen, paving the way for more complex life forms. The visual transition from a hellish, acidic wasteland to a green, verdant world would be a slow but awe-inspiring spectacle. Long-term, the timeline for terraforming Venus is measured in centuries, if not millennia. Initial atmospheric processing could take hundreds of years, followed by the gradual introduction of plant life. Over time, the planet's surface would cool and the pressure would decrease, making it possible for humans to walk on the surface without protective gear. Water, possibly harvested from asteroids or comets, could be introduced to create oceans and support more complex ecosystems. The end result would be a world that, while not an exact replica of Earth, could offer a new home for humanity and other life forms. The icy promise of Europa. Europa, one of Jupiter's largest moons, is a captivating enigma. Beneath its icy crust, scientists strongly suspect a global ocean of liquid water, making it one of the most promising candidates for potential habitability in our solar system. This icy world, with its potential subsurface ocean, presents a unique challenge and opportunity for terraforming. The process would be vastly different from that of Mars or Venus, primarily due to Europa's icy surface and lack of a substantial atmosphere. To transform Europa into a habitable world, the initial focus would be on creating a sustainable atmosphere. This would involve a multi-step process, starting with the introduction of greenhouse gases to trap heat and warm the moon's surface. The goal is to initiate a runaway greenhouse effect, similar to what is believed to have happened on Venus, but in a controlled manner. This would lead to the melting of Europa's icy surface, releasing water vapor into the atmosphere. Over time, this water vapor could condense and form a liquid water ocean on the surface, creating a more Earth-like environment. The transition from barren to green would be a slow and complex process. Initially, the surface would be covered in a layer of liquid water, which would eventually freeze if not maintained. To prevent this, continuous heating would be required, possibly through orbital mirrors or other advanced technologies. Once a stable liquid water ocean is established, the next step would be to introduce life. This could involve seeding the ocean with extremophile organisms, which are known for their ability to survive in harsh environments. Over time, these organisms could potentially evolve and diversify, leading to a more complex ecosystem. Atmospheric processing would be a crucial aspect of terraforming Europa. The initial atmosphere, primarily composed of water vapor, would need to be enriched with other gases to support life. This could involve introducing nitrogen and oxygen, possibly through the importation of volatile-rich materials from other celestial bodies. The atmosphere would also need to be protected from Jupiter's intense radiation, which could be achieved through the use of magnetic shields or other advanced technologies. Over time, the atmosphere could become self-sustaining, with life forms contributing to the cycling of gases. The long-term timeline for terraforming Europa would be measured in centuries, if not millennia. The process would involve numerous challenges and setbacks, requiring continuous monitoring and adjustment. However, the potential rewards are immense. A habitable Europa could serve as a stepping stone for further exploration and colonization of the outer solar system. It could also provide valuable insights into the origins of life and the potential for life elsewhere in the universe. The icy promise of Europa is a testament to human ingenuity and our relentless pursuit of knowledge and exploration. Titan, Saturn's enigmatic moon. Titan, the largest moon of Saturn, presents a fascinating canvas for terraforming due to its rich organic chemistry and substantial atmosphere. Unlike the airless, desolate moons of other planets, Titan boasts a dense atmosphere primarily composed of nitrogen, with a smoggy haze of hydrocarbons. This atmosphere, though toxic to humans, offers a starting point for atmospheric processing. To make Titan habitable, the first step would involve breaking down the abundant nitrogen and methane in the atmosphere. Catalytic converters or other advanced technologies could convert these compounds into more breathable gases, like oxygen. The process would be slow, taking centuries, but the end result could be a breathable atmosphere. The surface of Titan is a frozen, barren landscape, with temperatures around -290 degrees Fahrenheit, -179 degrees Celsius. To transform this icy expanse into a green, habitable world, the introduction of heat and liquid water would be essential. Orbital mirrors or greenhouse gases could be used to trap heat and raise temperatures. Once the ice begins to melt, liquid water would flow, creating rivers, lakes, and possibly even oceans. The presence of liquid water would be a game changer, as it would support the growth of Earth-like plants and microorganisms. Over millennia, the landscape would evolve dramatically. The initial introduction of plant life, either through seeds or genetically modified organisms designed to thrive in Titan's unique environment, would kickstart an ecosystem. These plants would produce oxygen through photosynthesis, further enriching the atmosphere. The once barren, orange-hued landscape would gradually turn green as vegetation spread across the surface. Animals and other life forms could then be introduced, creating a complex, self-sustaining biosphere. The transformation would be a testament to human ingenuity and our ability to reshape even the most inhospitable environments. The moons of Jupiter, Europa, Ganymede, Callisto. Jupiter's moons, Europa, Ganymede, and Callisto, present intriguing possibilities for terraforming, each with unique characteristics and challenges. Europa, with its vast subsurface ocean, offers a potential habitat beneath its icy surface. Ganymede, the largest moon in the solar system, boasts a magnetic field and possible subsurface oceans. Callisto, the outermost of the Galilean moons, is relatively undisturbed by Jupiter's radiation, making it a prime candidate for long-term habitation. To transform these moons into habitable worlds, atmospheric processing is crucial. Europa's thin oxygen atmosphere could be thickened by releasing gases from its subsurface ocean. This might involve drilling through the ice and releasing trapped gases, or using orbital mirrors to heat specific areas and trigger geological activity. Ganymede's tenuous oxygen atmosphere could be augmented by importing volatiles from other bodies or extracting them from its subsurface. Callisto's negligible atmosphere would require a complete overhaul, potentially through a process called atmospheric seeding, where gases are introduced to create a breathable environment. Visualizing the long-term timeline, the transformation of these moons would be a multi-generational endeavor. Initially, robotic missions would lay the groundwork, establishing infrastructure and initiating atmospheric processing. Over centuries, these moons could be encased in massive domes or enclosed habitats, allowing for the introduction of Earth-based flora and fauna. The process would involve careful ecological engineering, ensuring that introduced species could thrive and create a sustainable biosphere. Eventually, the moons could resemble Earth-like worlds, with lush landscapes and diverse ecosystems. The transition from barren to green would be a gradual process, marked by milestones such as the first signs of plant growth, the establishment of animal life, and the creation of stable water cycles. Each moon would present unique challenges and opportunities. Europa's subsurface ocean could support aquatic life, while its icy surface might be transformed into vast, Earth-like seas. Ganymede's magnetic field could protect its surface from solar radiation, fostering the development of complex ecosystems. Callisto's stable environment could make it an ideal location for large-scale agriculture and settlement. Through careful planning and technological innovation, these moons could one day become vibrant, habitable worlds. Enceladus, a hidden ocean world. Beneath its icy crust, Enceladus harbors a global ocean of liquid water, making it one of the most promising candidates for potential habitability in our solar system. This hidden ocean is kept liquid by tidal heating, a process where gravitational forces from Saturn deform the moon, generating heat. The ocean's existence was first hinted at by the Cassini spacecraft, which observed geysers of water vapor and ice erupting from the moon's south polar region. These geysers provide a tantalizing glimpse into the composition of Enceladus' subsurface ocean, which contains organic compounds and salts, suggesting the possibility of a habitable environment. Transforming Enceladus into a habitable world would be a monumental task, but the presence of liquid water and organic compounds provides a promising starting point. The first step would involve establishing a sustainable energy source to power the terraforming process. Given Enceladus' proximity to Saturn, solar power would be limited, so alternative energy sources like nuclear or geothermal would be more viable. Once energy is secured, the focus would shift to atmospheric processing. Enceladus' current atmosphere is extremely thin, composed mostly of water vapor. To create a breathable atmosphere, we would need to introduce greenhouse gases like carbon dioxide and methane to trap heat and raise the surface temperature. Over time, the increased temperature would allow the ice to melt, releasing more water vapor into the atmosphere and creating a water cycle. This process would be slow, taking centuries or even millennia to complete. As the atmosphere thickens, it would begin to shield the surface from harmful radiation, making it safer for potential life forms. The introduction of microorganisms and plants would further enhance the terraforming process. These organisms could help convert atmospheric gases into oxygen, paving the way for a more Earth-like environment. However, the long-term timeline for terraforming Enceladus is uncertain, as it would depend on numerous factors, including technological advancements and our understanding of planetary engineering. Visualizing the transition from barren to green, Enceladus would first see the emergence of microbial life, thriving in the warm, mineral-rich waters of the subsurface ocean. As the atmosphere thickens and the surface temperature rises, simple plant life could be introduced, adapting to the harsh conditions. Over time, these plants would spread, covering the icy surface with patches of green. The introduction of more complex life forms would follow, creating a diverse ecosystem. The once hidden ocean world would become a vibrant, habitable planet, teeming with life. However, this vision is purely speculative, as our current understanding of planetary engineering is still in its infancy. The journey to making Enceladus habitable would be a testament to human ingenuity and our quest to explore the unknown. The asteroid belt, a resource goldmine. Nestled between the orbits of Mars and Jupiter, the asteroid belt is a vast, dynamic region teeming with ancient rocks and minerals. These celestial bodies, remnants from the solar system's formation, offer a treasure trove of resources that could be instrumental in terraforming endeavors. The belt is estimated to contain millions of asteroids, with a combined mass about 4% of that of the Moon. This wealth of material could be harnessed to create new worlds, providing the necessary building blocks for infrastructure, atmosphere, and even water. To transform a barren world into a green, habitable one, atmospheric processing is a critical step. Asteroids can be rich in volatile compounds like water, carbon dioxide, and nitrogen, which are essential for creating a breathable atmosphere. By mining these resources, we can extract and process these volatiles, releasing them into the target planet's or moon's atmosphere. For instance, water can be split into hydrogen and oxygen, the latter being vital for human respiration. Carbon dioxide can help to initiate a greenhouse effect, warming the planet and allowing for liquid water to exist on its surface. Nitrogen, a key component of Earth's atmosphere, can be used to dilute oxygen to safe levels and provide the necessary pressure for human habitation. The timeline for such a transformation is staggering. Initial stages involve robotic missions to survey and mine asteroids, a process that could take decades. Once resources are extracted, they must be transported to the target world, processed, and released into the atmosphere. This could take centuries, as the atmosphere needs time to stabilize and support life. Over millennia, the planet's surface could begin to change, with water vapor forming clouds and eventually precipitating as rain. This rain would carve rivers, fill lakes, and nourish the soil, turning a barren wasteland into a lush, green landscape. The process is slow, but with the right resources and technology, it's a journey that could one day lead to a new, habitable world. The Oort cloud, a distant frontier. Nestled at the outer reaches of our solar system, the Oort cloud is a vast, spherical shell of icy objects that marks the boundary between our sun's influence and the interstellar void. This distant frontier, stretching from about 20 to 200 astronomical units (AU) from the sun, is a treasure trove of cometary nuclei, each a potential building block for terraforming endeavors. The Oort cloud's objects are remnants from the solar system's formation, composed primarily of water ice, methane, and ammonia. Their sheer numbers and composition make them an attractive resource for future terraforming projects. To transform a barren world into a green, habitable one, atmospheric processing is a crucial step. The Oort cloud's icy bodies can be harnessed to provide the necessary volatiles, such as water and carbon dioxide, to create a sustainable atmosphere. By redirecting these objects towards a target planet or moon, their icy contents can be released, seeding the atmosphere with vital compounds. Over time, these gases can be further processed and manipulated to achieve a balanced, Earth-like atmosphere. The long-term timeline for this process is measured in centuries, as the gradual accumulation of volatiles and the slow evolution of the atmosphere take place. Visualizing the transition from barren to green involves envisioning a world where the initial, thin atmosphere is gradually thickened and enriched. As more volatiles are introduced, the planet's surface begins to warm, allowing for the formation of liquid water and the potential for life. The once frozen, desolate landscape starts to thaw, revealing new geological features and paving the way for the introduction of plant life. Over time, the planet's surface becomes greener as vegetation takes hold and spreads, transforming the world into a lush, habitable oasis. This process is not instantaneous, but rather a slow, deliberate evolution that requires careful planning and execution. The science of terraforming, a grand design. Terraforming, the process of transforming a barren, inhospitable planet or moon into a habitable world, is a grand design that blends science, engineering, and a touch of audacity. At its core, terraforming involves altering the environment of a celestial body to mimic Earth's conditions, making it suitable for human life. This ambitious endeavor requires a deep understanding of planetary science, atmospheric dynamics, and ecological engineering. The journey from a desolate landscape to a lush, green world is a complex and multifaceted process that involves several key steps. One of the primary challenges in terraforming is atmospheric processing. Many potential candidates for terraforming, such as Mars or Venus, have atmospheres that are vastly different from Earth's. Mars, for instance, has a thin atmosphere composed mostly of carbon dioxide, with surface pressures far below what humans can tolerate. To make Mars habitable, scientists propose introducing greenhouse gases to warm the planet and thicken its atmosphere. This could be achieved by releasing large amounts of carbon dioxide from the planet's polar caps or by importing greenhouse gases from other sources. Over time, this process would raise the surface temperature, allowing for the melting of ice deposits and the creation of liquid water. The transition from barren to green involves a series of interconnected steps. Once the atmosphere is thickened and the temperature rises, the next step is to introduce microorganisms and plants that can survive in the new environment. These organisms would begin the process of terraforming the soil, making it fertile and capable of supporting more complex life forms. Algae and lichens, for example, are often suggested as pioneer species because they can thrive in harsh conditions and contribute to the development of a sustainable ecosystem. As the ecosystem becomes more complex, it would eventually support animal life, culminating in a self-sustaining biosphere. Visualizing the long-term timeline of terraforming is a fascinating exercise. The process is not measured in years, but in centuries or even millennia. Initial atmospheric modifications could take decades to show significant results. The introduction of plant life and the establishment of a stable ecosystem would require careful monitoring and adjustments over generations. The ultimate goal is to create a world that can support human life without the need for extensive technological intervention. This grand design is not just about making another world habitable. It's about ensuring the survival and prosperity of humanity beyond Earth. The journey is long and fraught with challenges, but the potential rewards are immeasurable. Engineering the atmosphere, breathing life. Atmospheric processing is the cornerstone of terraforming, the key to unlocking a barren world's potential. It's a complex dance of chemistry and physics, aimed at creating an atmosphere that can support life as we know it. The process begins with the most basic of building blocks: carbon dioxide, nitrogen, and water vapor. These are the gases that will form the foundation of a breathable atmosphere, and they can be sourced from the target planet or moon itself. For instance, Mars has abundant CO2 in its atmosphere and ice caps, while the icy moons of Jupiter and Saturn hold vast reserves of water. The transformation doesn't happen overnight. It's a slow, meticulous process that can take centuries, even millennia. First, greenhouse gases like CO2 are used to warm the planet, triggering a runaway greenhouse effect. This melts ice caps and releases more gases into the atmosphere. On Mars, this could lead to the formation of a thicker atmosphere, one that can retain heat and allow liquid water to exist on the surface. It's a delicate balance, though. Too much warming, and you risk creating a Venus-like hellscape. Too little, and the planet remains a frozen wasteland. Once the planet is warm enough, the next step is to introduce life. Initially, this would be in the form of extremophile bacteria and algae, organisms that can thrive in harsh conditions. They would begin the process of converting CO2 into oxygen through photosynthesis. Over time, as these organisms proliferate and diversify, the atmosphere would slowly become richer in oxygen. This is a process that took billions of years on Earth, but with careful management, it could be accelerated on a terraformed world. The long-term timeline of atmospheric processing is a story of patience and perseverance. It's a journey from a barren, lifeless world to a lush, green paradise. Along the way, there would be setbacks and challenges. The atmosphere might become too rich in oxygen, leading to wildfires. Or it might not have enough, leading to a stagnant, lifeless ecosystem. But with careful management and constant monitoring, these challenges can be overcome. The result would be a world that's not just habitable, but thriving. A world that's truly alive. The art of weather control, shaping climates. Weather control on a planetary scale is a complex interplay of science and engineering, aiming to transform barren landscapes into habitable worlds. The process begins with atmospheric processing, a crucial step that involves altering the composition of a planet's atmosphere to support human life. This can include introducing greenhouse gases to warm a planet, or removing excess gases to cool it down. For instance, on Mars, releasing CO2 from the polar caps could thicken the atmosphere and increase surface temperatures, a vital first step in making the planet more Earth-like. The transition from barren to green is a gradual one, often taking centuries. Initially, the landscape is stark and inhospitable, with no visible signs of life. As the atmosphere begins to change, so too does the surface. Water, either from melted ice or delivered via comets, starts to flow, carving rivers and filling lakes. The first signs of green appear as hardy, genetically modified plants take root, their seeds carried by the wind or deliberately planted. These pioneers pave the way for more complex ecosystems as they convert atmospheric CO2 into oxygen, further enriching the air. Visualizing the long-term timeline of weather control involves understanding the feedback loops and tipping points that can accelerate or hinder progress. For example, as more plants colonize a planet, they reflect less sunlight and absorb more heat, further warming the planet. This can create a positive feedback loop, where the planet warms faster than expected. Conversely, the initial introduction of life can also trigger negative feedback loops, such as increased cloud formation that reflects sunlight away, cooling the planet. Navigating these complexities requires sophisticated climate models and constant monitoring, as well as the ability to intervene and adjust the process as needed. Engineering the climate also involves managing extreme weather events, which can be more frequent and intense on a planet undergoing terraforming. Dust storms, for instance, can be a significant challenge on Mars, where the thin atmosphere and low gravity allow particles to stay airborne for extended periods. To mitigate this, engineers might propose creating artificial magnetic fields to hold onto the atmosphere, or planting vegetation to stabilize the soil. Each solution presents its own set of challenges and trade-offs, highlighting the intricate nature of weather control. Hydroponics and beyond, cultivating life. Hydroponics, the soil-less cultivation of plants, is a cornerstone of terraforming efforts, offering a lifeline to barren worlds. This method involves growing plants in nutrient-rich solutions, allowing for precise control over their environment. On Mars, for instance, hydroponics could be the first step in transforming the red landscape into a green one. The initial stages would involve setting up enclosed, controlled environments where plants can thrive despite the harsh exterior conditions. These early hydroponic systems would likely focus on hardy, fast-growing species like leafy greens and certain vegetables, which can provide quick yields and support initial human settlements. Atmospheric processing is another critical aspect of cultivating life on other planets. Mars, with its thin atmosphere composed mostly of carbon dioxide, presents a unique challenge. Scientists propose using advanced technologies to convert this abundant CO2 into oxygen, a process that could be accelerated by introducing specific types of bacteria and algae. These microorganisms can thrive in the Martian soil, or regolith, and contribute to the gradual transformation of the atmosphere. Over time, as the oxygen levels rise, the planet's surface becomes more hospitable to a wider variety of plant life. This transition from barren to green is a slow but steady process, requiring patience and persistent effort. Visualizing the long-term timeline of terraforming involves envisioning a series of incremental steps. Initially, small-scale hydroponic systems would support early colonists, providing essential food and oxygen. As these systems expand and become more efficient, larger-scale agricultural projects could be undertaken. The introduction of genetically modified plants, designed to thrive in the specific conditions of the New World, would further accelerate the greening process. Over centuries, the cumulative effect of these efforts could lead to a self-sustaining ecosystem, where plants not only survive but flourish, paving the way for a truly habitable environment. The journey from a desolate landscape to a lush, green world is a testament to human ingenuity and perseverance. Genetic engineering, evolution's new dawn. Genetic engineering is revolutionizing our approach to terraforming, offering a toolkit to reshape life itself. Scientists are exploring ways to modify organisms to survive and thrive in the harsh conditions of other planets. This isn't just about moving life from one place to another. It's about redefining what life can be. For instance, researchers are working on extremophiles, organisms that can survive in extreme environments, by tweaking their DNA to make them even hardier. These genetically enhanced organisms could be the first green shoots on a barren world, kickstarting an entirely new ecosystem. Atmospheric processing is a critical part of this puzzle. To make a planet habitable, we need to create an atmosphere that supports life. Genetic engineering can help here too. Scientists are looking at ways to engineer microbes that can convert atmospheric gases into more breathable forms. For example, certain bacteria could be modified to convert carbon dioxide into oxygen, a process that would not only make the air safer to breathe, but also help to regulate the planet's climate. This is a slow process, but over time, these microbes could transform a thin, unbreathable atmosphere into something more like Earth's. The long-term timeline for terraforming is measured in centuries, if not millennia. It's a project that will span generations. Genetic engineering accelerates this process. By carefully selecting and modifying organisms, we can speed up the natural processes of evolution. For example, genetically engineered plants could be designed to grow faster and more efficiently in low-light conditions, helping to establish vegetation on a planet with a dimmer sun. Similarly, animals could be modified to survive on a diet of locally available nutrients, reducing the need for Earth-based imports. This is not a quick fix, but a long-term investment in the future of life beyond Earth. The transition from barren to green is a complex process, but genetic engineering is making it more achievable. It's not just about moving life from one place to another. It's about redefining what life can be. By carefully selecting and modifying organisms, we can create a new dawn for evolution, one that spans the stars. This is not a task for the faint-hearted, but for those willing to take on the challenge. The rewards could be immense. A green, habitable world, teeming with life, is not just a dream. It's a possibility, and genetic engineering is the key. Nanotechnology, the tiny architects. Nanotechnology, the manipulation of matter on an atomic or molecular scale, is poised to revolutionize the concept of terraforming. These tiny architects, often referred to as nanobots or nanites, could be programmed to perform a wide range of tasks, from breaking down harmful chemicals to constructing complex structures. The potential applications are vast and varied, offering a glimpse into a future where barren worlds are transformed into lush, habitable environments. Atmospheric processing is one of the most critical aspects of terraforming. Nanobots could be deployed to convert a planet's atmosphere into a breathable mix of gases. For instance, they could break down carbon dioxide into oxygen and carbon, effectively creating an Earth-like atmosphere. This process would not only make the air safe to breathe, but also support plant life, which is essential for long-term sustainability. Additionally, nanobots could remove harmful toxins and pollutants, ensuring a clean and healthy environment. The transformation from a barren wasteland to a green, thriving ecosystem would be a gradual process. Initially, the landscape would remain desolate, with nanobots working tirelessly to prepare the ground. Over time, the first signs of life would emerge as plants begin to take root. These pioneering species would pave the way for more complex ecosystems, eventually leading to a diverse and self-sustaining biosphere. The timeline for this transformation would depend on various factors, including the initial conditions of the planet and the efficiency of the nanobots. Long-term, the vision extends beyond mere survival. Nanotechnology could enable the creation of intricate structures, from sprawling cities to vast agricultural systems. These tiny architects could construct habitats tailored to human needs, complete with advanced infrastructure and sustainable energy sources. The end goal is not just to make other worlds habitable, but to create environments where life can flourish, much like on Earth. This ambitious endeavor highlights the incredible potential of nanotechnology in shaping the future of space exploration and colonization. Energy solutions, powering the future. The quest to make other worlds habitable hinges significantly on our ability to harness and utilize energy efficiently. Solar power, for instance, is a frontrunner due to its abundance and sustainability. On Mars, the solar constant is about 43% of what we enjoy on Earth, but advanced photovoltaic technologies could still make it viable. Picture vast arrays of solar panels dotting the red landscape, their surfaces gleaming under the weak Martian sun. Over time, these panels could power the initial stages of terraforming, from heating the atmosphere to supporting early greenhouse structures. Atmospheric processing is another critical area where energy plays a pivotal role. To make Mars' thin atmosphere denser and more Earth-like, we would need to release greenhouse gases trapped in the planet's soil and ice caps. This process requires substantial energy inputs. Nuclear power, with its high energy density and reliability, could be a game-changer here. Imagine compact nuclear reactors scattered across the Martian surface, providing the consistent energy needed to heat the atmosphere and trigger a greenhouse effect. Over centuries, this could lead to a significant increase in atmospheric pressure and temperature, paving the way for liquid water and, eventually, a more hospitable environment. The long-term timeline of terraforming is a testament to the enduring nature of energy solutions. Initial stages would involve setting up power infrastructure, followed by atmospheric processing and the introduction of plant life. Energy storage systems, such as advanced batteries or molten salt storage, would be essential to manage the intermittent nature of solar power. Over decades, these systems would support the gradual transformation of a barren landscape into a green, habitable world. The vision of a lush, Earth-like planet emerging from the desolate expanse of space is a powerful motivator, driving innovation in energy technologies that could benefit both space exploration and life on Earth. The psychological frontier, human adaptation. The concept of terraforming, or transforming a barren, inhospitable world into a habitable one, is not just a challenge of engineering and science. It's also a profound psychological journey for the humans involved. The transition from a desolate landscape to a green, Earth-like paradise is a slow, gradual process that spans generations. Initially, the environment would be harsh, with thin or toxic atmospheres, extreme temperatures, and a lack of familiar flora and fauna. Over time, as atmospheric processing begins, the air becomes breathable, temperatures moderate, and the first signs of life, like lichen and moss, appear. This transformation is not instantaneous. It's a marathon, not a sprint, and it requires a unique kind of resilience and adaptability from the humans who undertake it. Atmospheric processing is a critical step in this journey. On Mars, for instance, the atmosphere is about 100 times thinner than Earth's and composed mostly of carbon dioxide. To make it habitable, we would need to thicken the atmosphere and increase the percentage of oxygen. This could be achieved through a process called terraforming, where greenhouse gases are introduced to warm the planet, releasing CO2 and water vapor from the polar ice caps. Over time, this could lead to the formation of oceans and a more Earth-like atmosphere. However, this process would take centuries, if not millennia. The first settlers would live in domed habitats, watching as the world outside slowly transforms. They would be pioneers, not just of a new world, but of a new way of thinking. The long-term timeline of terraforming is a testament to human patience and perseverance. The first generation of settlers would likely never see the completion of their work. Instead, they would pass on their knowledge, their hopes, and their dreams to their children, who would in turn pass them on to theirs. It's a relay race across generations, each runner carrying the baton a little further towards the finish line. Along the way, there would be setbacks, challenges, and perhaps even tragedies. But there would also be triumphs, discoveries, and the slow, steady progress of a world being reborn. The psychological impact of this journey would be profound. It would require a sense of community, a shared purpose, and an unwavering belief in the future. It would be, in many ways, the ultimate test of human adaptability and resilience. The ethical dilemma: to terraform or not. Terraforming, the process of altering a planet or moon to be more Earth-like, presents a complex ethical dilemma. On one hand, it offers the promise of new homes for humanity, a solution to overpopulation, and a safeguard against extinction-level events. On the other, it raises profound questions about our responsibility towards other worlds and the potential consequences of our actions. Consider the transformation of a barren planet. Initially, it's a desolate landscape, devoid of life, with a thin or toxic atmosphere. Through atmospheric processing, we could introduce greenhouse gases to warm the planet, melt ice caps, and release water vapor. This would kickstart a process of planetary engineering, where the atmosphere gradually becomes denser, temperatures rise, and liquid water forms on the surface. Over centuries, this could lead to a lush, green world, capable of supporting life as we know it. The timeline for such a transformation is staggering. It could take hundreds, even thousands of years to make a planet truly habitable. During this time, we would need to continually monitor and adjust the planet's environment. We would also need to consider the long-term impacts. What happens to the planet's existing ecosystems, if any? How do we ensure that introduced life forms don't disrupt the planet's natural balance? These are not trivial questions, and they demand careful consideration. Moreover, terraforming raises ethical questions about our relationship with the cosmos. Should we be altering other worlds to suit our needs, Or should we preserve them in their natural state? Some argue that terraforming is a form of cosmic vandalism, a reckless interference with the natural order. Others contend that it's our destiny as a species to spread out and inhabit other worlds. This debate is far from settled, and it's one that we must engage with as we venture further into the cosmos. The economic imperative, a new space economy. The concept of terraforming, once a staple of science fiction, is gradually inching towards reality. As humanity's gaze turns skyward, the economic potential of making other worlds habitable becomes increasingly apparent. The barren landscapes of Mars or the Moon, for instance, could one day be transformed into lush, green environments, not just for scientific curiosity, but for economic gain. This transition from desolate to verdant isn't just about making a new world look like Earth. It's about creating an environment where resources can be harnessed, industries can flourish, and economies can thrive. Atmospheric processing is a critical step in this transformation. Mars, with its thin atmosphere composed mostly of carbon dioxide, presents a unique challenge. Scientists propose using greenhouse gases to trap heat, gradually warming the planet and allowing CO2 ice to sublimate, thickening the atmosphere. This process could also release water vapor, contributing to the creation of a more Earth-like environment. On a longer timeline, introducing oxygen-producing organisms, like certain types of algae or bacteria, could further alter the atmosphere, making it breathable for humans. These changes wouldn't happen overnight. They would take centuries, if not millennia, to complete. Visualizing this long-term timeline involves understanding the scale of the undertaking. Initially, robotic missions would lay the groundwork, deploying atmospheric processors and setting up initial infrastructure. Over decades, these machines would slowly alter the planet's environment. Meanwhile, human missions would establish research outposts, gradually expanding as the atmosphere becomes more hospitable. The timeline would be marked by incremental changes, each building upon the last. Eventually, the red planet could become a green and blue dot in the solar system, a testament to human ingenuity and economic ambition. The economic imperative drives this vision. Space tourism, resource mining, and scientific research are just the beginning. A terraformed planet could host manufacturing hubs, agricultural centers, and even residential communities. The economic potential is vast, with new markets and industries emerging from the challenges and opportunities of living on another world. This new space economy wouldn't just benefit Earth, it could create a self-sustaining cycle of growth and development, fostering interplanetary trade and cooperation. The journey from barren to green isn't just about changing a planet's environment. It's about reshaping the future of humanity. The political landscape, interplanetary governance. The concept of interplanetary governance is as vast and complex as the cosmos itself. As humanity looks to terraform other worlds, the political landscape becomes a critical factor in shaping how these new environments are managed and governed. The transition from barren to green worlds involves not just technological feats, but also the establishment of political structures that can oversee and regulate these processes. This includes creating frameworks for resource allocation, environmental protection, and the rights of inhabitants, whether they are human settlers or indigenous life forms. Atmospheric processing is a key component of terraforming, and it requires international cooperation and governance. For instance, introducing greenhouse gases to thicken an atmosphere or using orbital mirrors to warm a planet's surface are large-scale operations that demand coordination among multiple stakeholders. Governance bodies would need to decide on the ethical use of such technologies, ensuring that they do not harm existing ecosystems or create unintended consequences. The long-term timeline of terraforming projects spans centuries, if not millennia. Governance structures must be adaptable, capable of evolving as new challenges and opportunities arise. This could involve the creation of interplanetary treaties, the establishment of governing councils with representatives from Earth and other colonies, and the development of legal systems that can operate across vast distances and time delays. Visualizing the political landscape of interplanetary governance involves imagining a future where Earth is no longer the sole center of human activity. New colonies on Mars. The moons of Jupiter or exoplanets and other star systems would each have their own unique political and cultural identities. Governance would need to balance the autonomy of these colonies with the need for overarching policies that ensure the sustainability and ethical management of terraforming efforts. For example, disputes over water rights, mineral resources, or the use of terraforming technologies could arise, necessitating robust legal and diplomatic frameworks. The political landscape of interplanetary governance is not just about managing the physical transformation of other worlds, but also about fostering a sense of shared responsibility and cooperation among all inhabitants of the solar system and beyond. The cultural shift, a multi-planetary society. The journey from a single-planet species to a multi-planetary society is not just a technological leap, it's a profound cultural shift. Picture this. The first human settlements on Mars, not as isolated outposts, but as thriving communities, their domes gradually replaced by terraformed landscapes. The transition from barren to green would be a slow, deliberate process. Initially, the red planet would be a stark contrast to Earth, with its thin, unbreathable atmosphere and stark, rocky terrain. Over centuries, however, the introduction of genetically modified plants and the release of greenhouse gases could thicken the atmosphere, raising temperatures and allowing liquid water to flow. The once barren landscape would begin to turn green, a testament to human ingenuity and perseverance. Atmospheric processing is a critical step in this transformation. On Mars, for instance, the atmosphere is primarily carbon dioxide, with only traces of oxygen. To make it habitable, we would need to convert this carbon dioxide into oxygen, a process that could be facilitated by introducing oxygen-producing organisms like cyanobacteria or using advanced technologies like the MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, device. This process would take time, but the result would be a breathable atmosphere, a crucial milestone in the cultural shift towards a multi-planetary society. The long-term timeline of this transition is difficult to predict, but it would likely span centuries. The first settlers would be pioneers, living in artificial environments, their lives dedicated to the slow process of terraforming. Over time, as the planet becomes more Earth-like, the culture of these settlers would evolve. They would develop a unique identity, shaped by their environment and their shared goal. This new culture would be a blend of Earth's cultural heritage and the innovative spirit of space exploration. It would be a culture that values resilience, adaptability, and a deep connection to the planet they are transforming. The transition from barren to green would be more than a physical change. It would be a cultural revolution, marking humanity's first steps towards becoming a truly multi-planetary species. The technological singularity, merging with the cosmos. The concept of terraforming, or making other worlds habitable, has long captivated human imagination. Central to this vision is the idea of a technological singularity, a point at which our technological growth becomes uncontrollable and irreversible, merging humanity with the cosmos. This merger isn't just about physical presence, but about integrating our technological and biological systems with the environments of other planets, creating a symbiotic relationship that transforms barren landscapes into thriving ecosystems. Atmospheric processing is a critical step in this transformation. Mars, for instance, has an atmosphere composed mostly of carbon dioxide with only traces of oxygen. To make it habitable, we would need to convert this carbon dioxide into oxygen, a process that could be accelerated using genetically engineered microorganisms or advanced chemical processes. These methods could also help to warm the planet, initiating a greenhouse effect that would melt the polar ice caps and release more carbon dioxide and water vapor into the atmosphere. Over time, this could create a more Earth-like environment, with a thicker atmosphere and liquid water on the surface. Visualizing this long-term timeline, the initial stages would involve robotic missions to set up the necessary infrastructure. These robots would be tasked with releasing greenhouse gases, perhaps from the planet's own resources, to initiate atmospheric changes. Following this, genetically modified plants could be introduced to convert carbon dioxide into oxygen and create a sustainable biosphere. This process wouldn't happen overnight. It would take centuries, if not millennia, to fully terraform a planet like Mars. However, the end result could be a lush, green world, teeming with life and potentially even supporting human settlements. The technological singularity aspect comes into play when considering the merging of human consciousness with these new environments. Through advancements in neural interfaces and artificial intelligence, humans could potentially upload their consciousness into digital forms, allowing them to exist and interact within these new worlds in ways that biological forms couldn't. This merger could also involve the integration of human-made systems with the natural processes of the planet, creating a harmonious balance that sustains life. It's a vision that pushes the boundaries of our current understanding, but remains a tantalizing possibility for the future. The ultimate goal, a galactic civilization. The vision of a galactic civilization, where humans thrive on worlds beyond Earth, is a compelling driver for terraforming efforts. This ultimate goal isn't just about survival. It's about flourishing, creating new homes among the stars, and ensuring the long-term prosperity of our species. To achieve this, we must transform barren, inhospitable planets into lush, Earth-like worlds. The journey from barren to green begins with understanding the target planet's resources and challenges. For instance, Mars, with its thin atmosphere and lack of liquid water on the surface, presents a stark contrast to Earth. Yet, it holds promise with its abundance of water ice, suitable temperatures, and a day length similar to ours. The process of greening Mars would involve releasing greenhouse gases to thicken the atmosphere, warming the planet, and allowing water to flow. Over time, this could lead to the formation of oceans, rivers, and lakes, setting the stage for plant life. Atmospheric processing is a critical step in this transformation. On Mars, for example, the atmosphere is about 100 times thinner than Earth's and composed mostly of carbon dioxide. To make it more Earth-like, we could introduce algae or other microorganisms that convert carbon dioxide into oxygen. This process, known as photosynthesis, is the foundation of life on Earth and could be the key to making other planets habitable. Additionally, we might need to import nitrogen, a crucial component of Earth's atmosphere, to create a breathable air mixture. This could involve transporting nitrogen-rich asteroids or comets to the target planet. The timeline for such atmospheric changes is long, spanning centuries or even millennia. However, the initial steps could be seen within a few decades as greenhouse gases take effect and the planet begins to warm. Visualizing the long-term timeline of terraforming involves understanding the complex interplay of geological, chemical, and biological processes. On a planet like Mars, the first signs of change might be subtle. A slight increase in atmospheric pressure, the formation of small pockets of liquid water, or the appearance of simple plant life. Over time, these changes would accelerate, leading to more dramatic transformations. Forests could spread across the landscape, oceans could form, and eventually, the planet could support complex ecosystems. The entire process would be a testament to human ingenuity and perseverance, a testament to our ability to shape our destiny among the stars. Yet, it's not just about making a planet habitable. It's about creating a new cradle for civilization, a new home for humanity. As we've journeyed through the cosmos of terraforming, let's take a moment to visualize the transformation. Imagine a barren, red landscape, devoid of life, slowly blanketed by a protective atmosphere. Over centuries, the once harsh surface softens as the first signs of green begin to emerge. Lichen, then moss, and eventually, the first trees take root. The air, once thin and unbreathable, thickens with life-giving oxygen. This is the power of terraforming, the art of breathing life into the lifeless. We've explored the key points: the introduction of greenhouse gases to warm a planet, the seeding of microbes to jumpstart an ecosystem, and the long-term management of a planet's climate. It's a process that takes not years, but centuries, a testament to human patience and perseverance. Now we turn to you. The future of terraforming isn't just in the hands of scientists and engineers. It's in the hands of dreamers, of explorers, of people who look up at the stars and see not just distant worlds, but potential homes. What role will you play in this grand adventure? As we conclude our journey today, remember, this is just the beginning. In our next video, we'll delve into the challenges and ethical considerations of terraforming. What happens when we encounter alien life? How do we balance the needs of Earth with the potential of other worlds? Join us as we continue to explore the final frontier. Until then, keep looking up, keep dreaming, and who knows, maybe one day, you'll be the one to plant the first tree on a new world.